here's the sheet that we got. Okay, this is the starting position. This is the position at which the washer hit the ground, and the beam was then coasting freely on top of the marker. This is the position at which the beam ended its motion when there weren't any washers sitting on it, and this is the position where it ended its motion when we did have a dozen washers or 10 washers or whatever it was setting on it. Okay? I've labeled a sheet, and let's just look at the way different parts are labeled. To document what I've got here, I said this is the acceleration by one washer, strings perpendicular to the beam. String won't always be perpendicular to the beam. We want to do this experiment with the string at various angles to the beam. We're limited on exactly what we can do there, because if we put too much force at an angle to the beam, it pulls the whole thing over. Beam length is 54 centimeters and has a mass of 280 grams. So there's some data about the beam. That's all going to be relevant. Then we come down here and we label this line start, we label this line washer hits floor. This one is labeled, this is where we end with 110 grams at 20 centimeters from the axis. The 110 grams is the total mass of those washers sitting on it at 20 centimeters from the axis. And this is the end when the beam was empty, and I should probably have said just a little bit more than just end. We've also labeled the time intervals. Okay, delta T1, delta T1 prime, that's going to correspond to the time interval, the 1.4 seconds. The delta T1 will be the 1.4 seconds on the unloaded beam, and the delta T1 prime will be the 2.2 seconds on the loaded beam. Similarly, we'll have a delta T2, which is 3.8 seconds for the unloaded beam, and a delta T2 prime, 2.4 seconds for the loaded beam. So we can see what the accelerations were here, velocities and so forth. We'll be able to determine all of these things. Now what we can do is place a sheet of paper over this figure. Now you can't see it too well because of the reflection with the camera and everything, but we can see the marks pretty well through the piece of paper. Now what I'll do is I'll put a mark corresponding to the first line on the paper. Then I'll move it over a little bit until the beginning point of this mark is at the second line, so that I can draw the second line here. Now these lines are a little wavy. I'll show you a good one that I did with a straight edge in a minute. Then I can move this over to the dotted line and so forth, and what I get is a figure like this. Where this is the starting position, this is the position at which the beam or the washers hit the floor, this is the ending position for the beam when it was unloaded, and this is the ending position for the beam when it was loaded. Now in order to get a better look at this and to orient it just a little bit more naturally, let's put it here. Now that's still not a real good orientation, but at least we can read what I've written on it. Okay? We're going to extend the starting position to make that the x-axis. We're going to call theta 1 the angle through which the beam rotated to the point where the washer hit the floor. We're going to call theta 2 the angle from the x-axis again, because all angles are going to be measured from the x-axis. We're going to call theta 2 the angle out to the ending position of the unloaded beam, and theta 2 prime the position to the end of the loaded beam. So now we have information about angles. Recall from the former that had we timed this, we would have information about time intervals between any of these events, between start and release for either the loaded or unloaded beam, and then between where the washer hit the floor and the coasting ended for either of the two beams.